we discussed the current. Then we discussed the current numerical methods for including their advantages and limitations. Then we introduced the neural network state, which is a promising route for designing variational wave functions. Lastly, we discussed the recently developed method, the backflow correction of the Green's function. We benchmark this method on Fermi-Hubbard-type models like the spinless Fermi TV model and the Fermi-Hubbard model, both on rectangular lattices. State-of-the-art energy precision is achieved. Okay, we start from introducing the quantum many-body problem. The quantum many-body problem is important in condensed matter physics. Several microscopic phenomena is described by many-body models. For example, understanding the mechanism of superconductivity, the quantum spin liquid, and the fractional quantum Hall effect. Furthermore, the simulation of quantum computing is actually solving the quantum many-body problem, as classical resources grow exponentially with respect to the number of qubits. A many-body state is represented in basis of configurations. To represent the many-body wave function, we need to do a mapping from the basis to the corresponding wave function coefficient. However, the number of bases is large. Taking a spin model as the example, a configuration contains the spin z value for each site. Because the spin on each site can be positive or negative, with the site number of n, the total configuration is 2 to the power of n, which is exponentially large. Although the total Hilbert space is exponentially large, a real physical state may not occupy all the Hilbert space. A quantum state with a limited entanglement, so-called error law entanglement, is distributed in a portion of the total Hilbert space, and many quantum states preserve symmetries. Thus, to represent a real quantum state, the effective Hilbert space is smaller than the total Hilbert space. Therefore, they can be approximated using classical methods in polynomial time. Some numerical methods are successful in solving the quantum many-body model, but these methods have their limitations. The exact diagonalization, ED, simply diagonizes the Hamiltonian matrix, and it gives accurate results, but it needs exponentially large classical resources. Taking a spin model as the example, without considering any symmetry, the qubit number is less than 30 for ED on nowadays supercomputers. The quantum Monte-Carlo QMC is accurate, but for models with sign problems, the computational complexity is extremely high. Novel microscopic phenomenon is usually caused by frustration or doping. The many-body model has severe sign problem. And the density matrix renormalization group, the DMRG, works for one-dimensional or quasi-one-dimensional systems. For two-dimensional systems, especially with periodic boundary conditions, the DMRG has too high complexity. The tensor network state, TNS, has high precision, but the complexity for periodic boundary condition is too high. Recently, neural network or machine learning is a promising route for designing wave functions. High energy precision were obtained by neural network states. For example, the highly frustrated model, like the J1J2 model, and wave function designs, like the Fermi-net, Pauli-net, accurately solves the multi-electron systems. Neural network states are flexible for Hamiltonian types, lattice types, and boundary conditions. For the Fermi-Hubbard model with periodic boundary conditions, the neural network state still has high complexity. A method without sign problem is the variational Monte-Carlo, which includes the Markov chain Monte-Carlo sampling of the designed wave function and optimizing the wave function based on gradient descent. The variational Monte-Carlo doesn't have sign problem, but it requires the designed wave function having sufficient quantum state representation ability. This slide shows the procedure of the variational Monte-Carlo optimization. In the Markov chain Monte-Carlo process, samples are collected based on the Metropolis-Hastings algorithm. Each sample is a configuration. When collecting a sample, the local energy ES and the local derivative OS are calculated and stored. After collecting sufficient samples, the energy expectation as well as gradients are calculated. Then we optimize variational parameters in the wave function based on the gradient descent method. Here we modify the gradient descent method by omitting absolute values and just adopting signs of gradients. Because of the limited Markov chain Monte-Carlo sample number, the absolute value of the gradient is difficult to be precisely obtained. However, the sign of the gradient is determined by a limited number of Monte-Carlo samples. Thus, we only use the sign of the gradient and applying a small step size eta. These procedures are repeated until the energy expectation converges. Ideally, the energy will converge to the lowest value, which is the ground energy regarded. In real cases, only using first-order gradient may not be sufficient. Thus, we may use the second-order optimization like the stochastic reconfiguration and so on. This slide shows the calculation of the local energy ES and the local derivative OS during the Markov chain Monte-Carlo sampling. For the local energy ES, wave function coefficients for the non-diagonal part of the Hamiltonian are calculated. The number of the non-diagonal coefficients is related to the Hamiltonian type and the lattice size. For a Hamiltonian with local couplings, for example, the Heisenberg model, there are lattice size magnitude of non-diagonal coefficients in one calculation of local energy. In local energy, all calculations are forward. For the local derivative OS, there is gradient respect to the WS, which needs backward calculations. The variational Monte-Carlo requires the wave function possessing a proper state representation ability. In principle, the mapping from the basis to the wave function coefficient is achievable by the variational function with sufficient parameters. However, when the lattice is too large, as denoted in the slide, in the sampling process, it's possible that the configuration is very far from the real wave function regime because of the randomness of Markov chain Monte-Carlo. Because it's impossible to explore the whole Hilbert space classically, a function with a proper state representation ability should give a moderate WS when inputting a configuration that a function has never seen. Therefore, a function too expressive will need the optimization stuck on local minima. This is the major challenge for designing variational wave functions, that the wave function should not be too expressive, meanwhile maintaining sufficient state representation ability. Because the neural network is a general function fitter, it can be used to fit the wave function. With a proper design, a neural network can represent the wave function on flexible Hamiltonian type and lattice type. Therefore, neural network states can overcome current methods' limitations on the coupling range in the Hamiltonian and the lattice boundary condition. Here is a demonstration of the variational Monte-Carlo using a convolutional neural network as the wave function, which was published in the year 2018. The wave function is a convolutional neural network with just 3 layers, a convolution layer, a max pooling layer, and a transposed convolution layer. The convolution filter size and the number in the first convolution layer is very important for state representation. And in the paper, we solved the frustrated J1, J2 model which has no range correlation. Thus, it is challenging to solve. Thus, the maximal filter size is as large as the lattice size. Here, in this slide, we try to solve the spin model, which describes the Rydberg atom array. The Rydberg atom array is a type of quantum computer that can simulate many-body physics with up to 1,000 qubits. The Hamiltonian describing the Rydberg array is similar to a transverse field Ising model. The difference is the non-range interactions. The tunable parameters in the Hamiltonian is the coupling strength for the non-range interactions, V. The right figure denotes the energy convergence of convolutional neural network wave function for solving the Rydberg array. For the Rydberg array, the correlation length is limited, thus it's closer to a classical system comparing to the J1J2 model. Therefore, a large convolution filter leads to overfitting. We choose the filter size as large as 3 by 3 and 128 filters, so the energy converges smoothly. We also investigate the spin density, which is the average spin value per site. The spin density pattern finally matches the experiment result after sufficient optimization steps. The neural network state is a powerful representation, and this table takes the frustrated J1J2 model as the example. From year 2018 to date, energy precision has been constantly improved. Thus, neural network states are promising for spin models. The previous success are for spin models, which can be treated as hardcore bosons. For Fermi-Hubbard-type models, a requirement is preserving the anti-symmetry of Fermis. Thus, the Hartree-Fock-like Slater determinant is necessary. Several methods have improved the Hartree-Fock Slater determinant, like the wave function backflow correction. However, the improvement is still limited. In this section, I will introduce our recent work. We start from the Green's function and using the backflow corrections to improve the Green's function. Because Green's functions are compact representations for correlations, which are contained in the ground energy. The Fermi-Hubbard-type models contain Hoping terms and interaction terms. When calculating the energy expectation of this Hamiltonian on the wave function, it is straightforward that Hoping terms are one-body correlations and the interaction terms are two-body correlations. Therefore, solving the ground energy is equivalent to achieving these correlations. The correlation is naturally represented by the Green's function. Now, here is the definition of a one-body Green's function. It contains two particles, I and j prime. When taking the limit of t prime equals t, the one-body Green's function can represent a Hoping term in the Hamiltonian. Similarly, an interaction term can be represented by a two-body Green's function. Based on the one-body and the two-body Green's function are connected by the equation of motion, it is possible to solve the ground energy using Green's functions. Previous literature has demonstrated that accurate ground energies were achievable with Green's functions, but without wave functions. This is quite useful for cases those don't need wave functions, such as building potential energy surface of molecules. For the Fermi-Hubbard-type model, the wave function is important because energy values are very similar between the ground state and the metastable states. We need the wave function to identify the ground state property. In this work, we aim to design a variational wave function based on correlations. Recalling the wave function used in the variational Monte-Carlo during the sampling, the calculation of local energy and the local derivative, only values proportional to the wave function coefficients are used. Thus, we don't care about the normalization factor of the wave function. When we start building the wave function using correlations, we need to extract the wave function coefficient from the density matrix. An element of the density matrix under two configurations, S and S prime, is then the product of the coefficients Ws and Ws prime. The density matrix element is represented by the unbounded Green's function under the ground state. The unbounded Green's function contains n creating and destroying operators. Meanwhile, creating operators represent the configuration S prime, and destroying operators represent the configuration S. Based on mean field theory, the unbounded Green's function is represented by the determinant of the one-bounded Green's function, as depicted in the slide. Each matrix element is a one-bounded Green's function that propagates from the configuration on one side to the configuration on another side. This determinant is an exact representation for free electrons, namely electrons without interactions. For electrons under strong interactions, such representation is not sufficient. To represent electrons with interactions, we also need this format of determinant in order to maintain the antisymmetry of fermions. One way to improve this is adding super-exchange terms into one-bounded Green's functions. Namely, each one-bounded Green's function contains correlations on other sides rather than they already have two sides. The improved one-bounded Green's function is denoted as GB in the slide. Here we denote how the backflow correction is performed for the one-bounded Green's function. For a one-bounded Green's function, it associates with two sides, such as I and J in the slide. The backflow correction adds information of other sides into the one-bounded Green's function. One straightforward way is to put all sides into the one-bounded Green's function. However, this will cause redundant computations for the Hamiltonian with only local couplings. As denoted in the figure, we take nearest neighbors of both site I and site J for backflow corrections. This is suitable for the Hubbard-type Hamiltonian with only nearest neighbor hopings and interactions. The summation in the backflow correction is performed on all sides. Those are nearest neighbors of site I and site J. Here we demonstrate one term in the summation. When choosing a specific site for backflow correction, two additional one-bounded Green's functions are considered. They are the propagator from the site to site J and the propagator from site I to the site. In the gradient descent optimization, we treat both coefficients and one-bounded Green's function in the backflow corrected one-bounded Green's function as variational parameters and let the optimization to determine their values. Okay, so now let's look at numerical results. Firstly, we test our method on the spinless fermions TV model. The Hamiltonian contains hoping terms and interaction terms between adjacent sites. The lattice size is 10 by 10 and the particle number is half of the site number. For the spinless case, maximal occupation per site is 1. Both directions are open boundary conditions. The reference energy is obtained by the tensor network state. The bound dimension is 8 and the contraction dimension is 32. The Hartree-Fock result is obtained by the one-bounded Green's function without any backflow term. We benchmark on the V is 0.45, 1 and 2. The phase transition point is near the V is 0.45. And P equals 0 is the result for the gradient descent, and P is 1 is one nasal step for the P0 result. We firstly optimize the Hartree-Fock state. The Hartree-Fock converges rapidly. Then we add backflow terms into the one-bounded Green's function and continue the optimization with the initial energy from the Hartree-Fock. The table denotes the energy comparison from P is 0 results. Our method has high energy precision comparing to tensor networks. At the phase transition point, our method even has lower energy than the tensor network state. This may be due to the limited bound dimension of the tensor network. The energy difference between P is 0 and P is 1 reveals the convergence of the optimization. Because of the small energy difference, optimizations are treated as fully converged. The figure below denotes the energy convergence for the V is 1 case. The initial energy is from the Hartree fork, and therefore the energy convergence is achieved by backflow terms. The Fermi-Hubbard model is a more challenging case. Because of the spin, the maximal occupation per site is 2, thus a larger Hilbert space than the TV model. The Hamiltonian contains hopping terms and on-site interaction terms. In the table, n is the Finite number, which is the ratio of the particle number over the site number. All calculations are based on periodic boundary conditions. The ratio of U and T is 8 for all calculations. For the half-filling case, that the particle number is the same as site number, the model is similar to a Heisenberg model, which has antiferromagnetic order, which is easy to solve. For the Finite number of 0.875, it is more challenging to solve. The table denotes energy comparisons. The reference energy 1 is from neural network Backflow. It accepts information of all sites for backflow terms. In our method, we only take nearest neighbors of sites appeared in the one-body Green's function. The reference energy 2 is from the hidden Fermi-Slater determinant, which is also a neural network state. It gives state-of-the-art energy results for periodic boundary conditions. From energy comparisons, it is concluded that our method gives high energy precision. The figure denotes energy comparisons. From the figure, our method gives lower energy values than neural network backflow for all lattice sizes. After one nasal step, our method gives lower energy values than the hidden Fermi-Slater determinant. We also investigate the spin density of the ground state. To break the translational symmetry, we apply a pin field on the short edge of the lattice. From state-of-the-art auxiliary field quantum Monte-Carlo calculations, the ground state should be the stripe order. From the figure, we successfully reproduced the stripe order, especially for the 4×20 case. Our energy is even lower than the DMRG result. We also benchmark on the lattice as large as 8×16, totally 128 sites. The stripe order is similar to the lattice size of 4×16. Therefore, our method has sufficient energy precision to reproduce the order of the ground state. In conclusion, the backflow correction for one-body Green's function is a highly efficient and a representative method for representing quantum many-body states. It can be used to seriously investigate the Fermi-Hubbard model with or without next nearest neighbor hopping terms. It can also be used to improve current state-of-the-art method like the auxiliary field quantum Monte-Carlo. It can also be used as the solver in the dynamic mean field calculation. Furthermore, it can also be used to solve small moleculars. Okay. Thank you.
Oh, thank you. Okay, so it's a quite short talk. Okay, so please go ahead. Vlad, you have questions?
Yeah, this is very interesting and very beautiful work. I would like to ask, I remember from the past that people talked about these backflow corrections in the context of the Hubbard model and the Gutzwiller variational wave